All right, so this is the first lecture for Physics 1. And we start doing the typical Chalk Talk notes lectures at section 1.4 in matter and interactions. And here is where we introduce vectors, because we live in a three-dimensional world. Okay, we live in a multi-dimensional world, but classical physics typically takes place in 3 dimensions of space, 4 if you count time, but we're not going to be doing 4-vector physics here. And so if we're going to do interactions in 3 dimensions, we need to learn about vectors, which are basically numbers in 3 dimensions. We'll be doing standard arithmetic and algebra with them. All right, so let's go 3D. So in our everyday life, you move in 3 directions: X, Y, and Z. X, Y, and Z. So typically speaking, our x-axis is here. Our y-axis is typically denoted as up and down, though not always. And then your z-axis comes out of the page and into the page. And so you could go this way, you go up and down, or you can go in and out. So in the motion that we'll be looking at, all of these are available directions that you could go in, so we need a way to describe them. We need vectors. So this is things in 3D, like position or velocity. So, and we can use vectors to describe these interactions resulting from a change in velocity or position. So the symbol for a vector you'll see this is a vector, or you might also see R with an actual little arrow. And then in more advanced physics textbooks, you'll see that vectors are bolded like this. So for example, I'm teaching modern physics this semester, and vector notation in that book, all the vectors are bolded. So in your book, you'll see this. This is my notation. And more advanced books. So if you see this, you are dealing with a vector, which means it has a directional component. So for a 3D vector, or a spatial vector that we would be dealing with in the Cartesian coordinate plane, we would have an x component, a y component, and a z component. So for example, if we have our vector r1 is equal to 4 minus 2, 10 meters. So typically you put the unit on the outside, or you can put the unit with each component, and it will have the same units within the vector. So if we were to plot this particular vector, so R typically denotes position. So in this case, what that's saying is you're going over positive 4 in x, you are going down minus 2 in y, and this is 3 dimensions, so we'd be going positive 10. So then this would be where R1 is. So if we are drawing vectors, it's very rare that I would have you draw in 3 dimensions. Typically, I'll stick with a 2-dimensional drawing for a vector, but for calculation, 3 dimensions are fair game. So this is a position vector. It tells you where in 3-dimensional space the object is. I already said velocity is also a vector because it's how fast and in what direction. So something is a vector quantity if you also ask in what direction or in what location. So you could have a velocity minus 7.2 minus 3.5 meters per second. So in terms of how you'd think about this, it's slowing down in x, or it Yeah, it's slowing down in x, slowing down in y, and speeding up in z. So this would be a velocity vector. So something you've noticed with both of these vectors, both have units. Units are very important in physics. So this is a physical world. We measure quantities. So if I was to say the velocity is going 1, 10, 72, that doesn't make any sense. Meters per second, miles per hour, fortnights per furlong. We need to know these things. So always ask for units when you're given a quantity. Every once in a while, we'll see a few things that are unitless, but by and large, most things have quantities. And by the way, in my class, I value units so much, are so important, that I take off 2 points. If they are missing or wrong in an answer. I only take off 1 point if your final number quantity is wrong. So that's how important units are, because units are what helps us make sense of the physical world. Okay, so we've gotten the idea of what vectors are in terms of they are a number that goes in 3 dimensions that we can do algebra with and etc. So let's look at some really common vector quantities that we're going to work with, just to get an idea of why we do vectors and just how prevalent they are in this beautiful world we live in. Naturally, this is not an all-encompassing list. This is just, so we will do position. Where in space are you? Typically denoted with an R. Velocity. How fast and in what direction? Acceleration. Are you speeding up, slowing down, and in what direction? Momentum. Mass times velocity. Very important in physics. It's denoted with a P. And then we'll look at the rate of change of momentum, which you'll either think of it as delta P over delta T or the time-based derivative of momentum. Force is a 3-dimensional quantity, so you could force in different directions. Angular momentum, so think spin. Torque, nice little tau. Electric field, we just wrapped up physics 2. We do lots of fields. Those are in 3 dimensions. And a magnetic field is also in 3 dimensions. Okay, and all of these have units associated with them. So some of the units you've already seen, positions typically in meters, acceleration meters per second, velocity meters per second, acceleration meters per second squared, etc. And the rest of these we will learn the units as we go. Okay, so this is sort of a look of the future of vectors in this class. Now let's come back to the present and let's just get really nice and comfortable with vectors since we're going to be using them a lot. And we're going to start with position vectors. And we'll get into all of the lovely vector conventions. So, we will be working in the Cartesian coordinate system in this class. This is the coordinate system that most of you are likely the most familiar with. And this is the one I just showed you. So X, Y, and Z. So you're probably really familiar with the XY plane. There are other coordinate systems, and you would certainly see them in more advanced classes, but we mostly stick with the Cartesian coordinate system. I'm just going to note, because you might see this in a different physics book or a math book, it's not uncommon to see Z where you'd normally see Y, and then Y would be coming out. So also common. So, and when you set up your coordinate system for a particular problem that you're solving, what is important is that you label it. So if you're going with anything other than this convention here, then I would expect to see a little picture just letting me know what you're doing. And as long as you're consistent and you do everything to that system, that's perfectly legal to do that. Okay, so if you're going to draw a position vector, let's go ahead. I'm going to get fresh paper. Let's walk through what that looks like. So in physics, measurements are always made relative to something. So when you're dealing with the Cartesian coordinates, it's relative to the origin. And that's, of course, where X, Y, and Z meet. It's also the 0 vector, sometimes denoted with a 0 with a little vector sign over top. Okay, so if we had a position vector, R is equal to 4, 5, 3 meters. I think this is going to be the last three-dimensional vector that I try to draw today, I hope. So we have our Y, we have our X, and we have our Z coming out. Okay, so what we would do, so we're coming over 1, 2, 3, 4 in X, so our X is equal to 4 meters. Then our Y, 1, 2, 3, 4, 5. So our Y is equal to 5. And then in Z, it's equal to 3. Just enough colors, 1, 2, 3. R2 is equal to 3. So then when you draw your vector, which I will draw in purple, so you would see that it would come down and we can see that we've got a little triangle going on here. So if you think about the Pythagorean theorem, where we were looking at triangles in 2 dimensions, now we're just looking at a triangle in 3 dimensions. So with a position vector, the tail, so that's the part of the vector that doesn't have the arrow, starts at the origin, and then the arrow goes where the position is. So in this case, you can see it starting at 0, and the position here is coming out 3 in Z, up 5 in Y, and over 4 in X. Now, you might see a system where it's not relative to the origin, and those, we'll talk about how to draw those when we get to them. Okay, so that is the convention for drawing a position vector. So each number in a vector is called a component. So these are sometimes denoted with subscripts. And I'll show you what I mean. So for example, the velocity vector, you might see, let's try this again, v sub x, v sub y, v sub z. This is velocity. So each one of these components are scalars. So this is the velocity in x, velocity in y, velocity in z. And so these are the components. You have the x component, the y component, and the z component. Then for position, you might see it denoted r sub x, r sub y, r sub z, or with position, you'll also see x, y, and z. So these are two generic position vectors, just like that is a generic velocity vector. And the units will hold for each of these components. So for example, if we have a velocity vector 12.2 minus 15.4 minus 8 meters per second, then if we want to isolate Vx, so it's not a vector, so it doesn't get a vector symbol, then that's 12.2 meters per second. So not a vector, but still has units. Okay, so, oh, and by the way, the origin vector technically also has units. So origin 0, 0 equals 0 equals, yeah. This would be, for position, it might be in meters. And if this was for velocity, 0 implies an object at rest. Okay, so now that we know how to draw a position, let's look at how we draw a velocity vector. Now I'm going to switch into two-dimensional drawings, which is most of the drawings you'll be doing, but we still want to think in 3 dimensions. A big reason why I teach vectors is to help you think in 3 dimensions, because that's vital to the field of physics. So let's look at the drawing conventions for velocity. So the tail is at the object's location, and the arrow points in the direction of motion. So for example, if we had a velocity vector 1, 1, 0 meters per second, and let's say the object starts at, let's make it easy, 1, 1, 0 meters. So the object is located here, and it's accelerating 1 meter per second in y and 1 meter per second in x. So then this would be what the velocity vector would look like. So in this case, this is indicating speed and direction. Okay, so now I did say that not all position vectors are drawn from the origin. You could have a displacement vector. So displacement, we'll do a lot of this. This is basically how far have you moved and in what direction. So with the displacement vector, let's say you start at 0, 1, 0 meters, and go for a little walk, and then you end at 3, 2, 0 meters. Just going for a little walk. Okay. So for something like this, then what you do is you put the tail at your starting position, So it's 0 in x, 1 in y. So our tail goes here, and then you put your arrow at your ending position. So you're going to go over 1, 2, 3, and then up another one. And this is your displacement vector. So all right, so I've already said this word a couple of times, but what if something is not a three-dimensional quantity? So what do we use? So what if it's not 3D? So in other words, there's no direction with it. It's directionless, like me in college. Okay. Then we have what's known as a scalar. And these are one-dimensional numbers. So some examples of scalar quantities. So these are just, they have values, but not direction. So mass, you don't have mass in y. Temperature, speed, power, energy, and time. These are all physical quantities that are in one dimensions, so they've got a value and a unit associated with them, but no direction.